Well, good morning, everyone. Thank you for joining the talk today. As was just said, my research project is on the assessment of mass concrete thermal prediction methods and failure criteria. And today I will be introducing some of the novel models we've been working on and also present some case studies. So the broader goal of this project is to provide the Georgia Department of Transportation with best practice guidelines and recommendations for the construction of mass concrete projects and related thermal control measures. And one of the motivations of this project is this mass concrete structure that you see here. This is an abutment wall that was constructed as part of a state route relocation and widening in the city of Douglasville. And the wall is 6 feet in thickness, which makes it qualify as mass concrete in the state of Georgia. So an interesting fact about this wall is that it was built adjacent to a railroad, and according to the specifications of the Railway Association, the mixed design was not permitted to have any mineral additives such as like class F fly ash or slag. And for this reason, the mixed design that was adopted was a high heat mix, and it contained only OPC. In order to control the expected temperatures out of this mixed design, the contractors had to adopt two different cooling measures of the concrete. The first one was pre-cooling the concrete using liquid nitrogen, and the second one is embedding a cooling pipe system, as you can see here in the picture, through which chilled water runs in order to bring the temperatures down during hydration. And the maximum recorded temperature at the hottest part of the structure was around 130 degrees Fahrenheit, which is well below the limit of around 160 degrees Fahrenheit. Now, despite the success in controlling the temperature rise, the thermal control measures that were adopted in the structure were expensive. So pre-cooling using liquid nitrogen, for example, increased the cost by around $50 per cubic yard, and the post-cooling system increased the cost by around $80,000 per abutment wall, and they had several abutment walls on this project. Moreover, after sitting down and talking with the contractors, they told us that they prefer pre-cooling to post-cooling any day, since post-cooling has this adds some sorts of complexity to the construction process, which they would prefer not to go through. For this reason, what we had to do for GDOT is provide best practice guideline on and make recommendations about which thermal control measures they would need to do for future mass concrete projects in order to decrease both cost and complexity. And the first task was to accurately model mass concrete structures and propose some alternative mixed designs that are lower in heat than the conventional OPC concrete. The second task was to propose alternative modeling approaches to find the heat of hydration of the concrete. And the third task was to provide GDOT with thermal management tools that would be easy to use and implement in order to have a preliminary that would serve as preliminary decision-making tools. So let's start with the first task. In order to see which models work best for mass concrete application, we had two different mid-scale experiments here at Georgia Tech. They were both 4 by 4 by 6 feet in dimensions. The first one was a type 1-2 cement, and there were no cooling measures adopted. As for the second one, it had a blended cementitious paste with 25% fly ash replacement, and we had the embedded cooling pipe system inside, as you can see. For the modeling of these elements, we used the most widely used 3-parameter exponential model, which is the current practice in the industry for mass concrete application. This model finds the heat of hydration and how it develops with time for a certain cementitious paste. We've applied this model to both mid-scale experiments, and using finite element software, we were able to find the internal temperatures at the maximum point in both structures. And we can see here the fits are in the dashed blue line. They do not match very well with the gray line, which is the sensor data. There is a lag in the temperature development up until around 16 hours, and then the temperature rise gets better. And this causes inaccuracy in predicting the time at which the maximum temperatures and maximum temperature differentials occur, which could lead to inaccurate prediction of cracking potential. Sorry about that. The prediction for the second mid-scale experiment was also not good. You can see that for the cooled experiment, the model was not able to capture the peak temperature. So we decided to propose an alternative modeling approach. We used experimental isothermal calorimetry to find heat of hydration of the cementitious pastes. And this procedure requires that we perform the test at different temperatures. Here I'm showing temperatures, curing temperatures ranging between 10 and 90 degrees Celsius. Of course, we do not have to do that many experiments. We can just do 3 representative ones. And we find the rate of heat release and the cumulative heat of hydration for a certain cementitious paste and all the materials that it contains. After doing so, we would need to create a mapping between cumulative heat of hydration, temperature, and rate of heat of hydration. And this mapping facilitates that if we have 2 out of 3 of these values, we can easily find the third one using this curve. And we can find the cumulative heat for a certain cementitious paste. This information is readily available in the literature. And we can calculate the corresponding temperature rise expected of a certain heat evolution by having information on the thermal properties of the concrete. So now we have these 2, we can come into the curve and find the third one for any 2 values. We can find the rate of heat of hydration, and now we have these different profiles. What's missing is time, but by performing more mathematical operations, we can actually find time from the information that we have, and we get these curves, which are representative of properties under mass concrete conditions or adiabatic conditions. So we use this curve instead of the 3-parameter exponential model in the finite element modeling. And these are the results in red, and we can see that they match much better than the 3-parameter exponential model for these 2 mid-scale experiments. So now that we've decided on a model to proceed with, we wanted to suggest other mixed designs that GDOT could have used or could use for future projects that would be lower in heat than the conventional type 1-2 cement. This one is the SR92 cement, and the dashed black line shows the strength requirement for that certain project. So this is the abutment wall cement, and this is the strength requirement for that abutment wall. And here are the mixes that we are proposing. Some have fly ash replacement, some have fly ash and blast furnace slag replacement, and this one is just a type 2 cement that is coarser than the typical type 1-2 cement. And we can see that concretes made with these pastes are satisfying the strength requirement, most of them at 28 days, and then the 45% fly ash replacement catches up at around 56 days. So in terms of compressive strength, all of the mixes that we are proposing work. Next, we wanted to see if we use the isothermal calorimetry modeling approach on the SR92 abutment wall, and if we assume that there's no post-cooling, so we're only pre-cooling using liquid nitrogen, what the results would be using these mixed designs. This is the maximum temperature profile, like the predicted one, and we can see that 4 mixes satisfy the limit that is in dashed, that's the dashed black line, which is pretty good. And also all of the mixes satisfy the maximum temperature differential limit up until around 7 days, which is the time of removal of insulation and formwork. And after that, there's a spike in the temperatures. The lowest ones are the 45% fly ash replacement and the coarser type 2 cement. So the conclusions that we came up from this part of the task is that first, GDOT could have, the contractors could have pre-cooled the structure a little bit further in order to have a wider range of mixed designs that could work. They could, of course, use an alternative mixed design than the OPC only mix. I know they had restrictions with respect to using SCMs, but they could have used a coarser cement. And finally, they could push back the time for removal of insulation and formwork a little bit, such that some of these mixes would satisfy the temperature differential. And GDOT were actually open to considering all of these recommendations, and they want us to do further analysis to see what other mixed designs could work for this purpose. The second task was to find alternative modeling approaches. So as I said, we have used isothermal calorimetry experiments to find heat of hydration, but it also remains important to have a modeling approach that is not experimental in case we want to investigate more mixes without doing experiments or in case the experiments are not readily available for everyone. So we have looked into kinetic models in the literature to see which one would work for this type of problem. And this was a very complicated process since the heat evolution curve of concrete or cement could be divided into 3 different phases, and each one is controlled by a different mechanism and would have a separate model to predict the heat evolution. And this would be further complicated when we add SEMs and other admixtures. So alternatively, we decided to look into computational artificial intelligence models. For this task, I have collected 400 plus different tests, isothermal calorimetry, heat of hydration tests for different cementitious pastes and at different temperatures. And this shows which features I have included in the prediction. We had some physical features such as time and temperature, some chemical characteristics of the cement and the SEMs that we used, and the phase composition and fineness of the materials. And for the SEMs, I have included fly ash, slag, and limestone. For the modeling, I have used Gaussian process regression, which is a non-parametric machine learning methodology, which assumes that similar inputs should have similar outputs. And I have split the database into 80-20 training and testing sets. So this means that 326 mixes would be used to build the data, to build the model, and the remaining would be used to test it. And these are some of the results that I have got. The solid blue line shows the experimental results, and the blue circles are the prediction. The gray lines are the confidence interval limits, and the red squares just show how the root mean square error evolves with time. As we can see here, for these 4 different mixes, the results are very, very good using the machine learning prediction. We have an OPC only mix at room temperature. We have a 20% fly ash replacement at 50 degrees Celsius curing temperature. We also have blast furnace slag replacement and the limestone cement. And the model is doing really well for all of these different mixes and also at the different temperatures.
You have 2 minutes left, Luna.
Okay, thank you. This here shows how the errors for the different testing sets, the different testing mixes propagates with time. And you can see that the error does not increase with time. It's pretty constant. There are some stowaways, which probably belong to a few mixed designs that did not do well in the prediction, but these are just like 2 of them. And the R squared for the testing data set was around 96%. I have used the model to see how it would do on the first mid-scale experiment. So I extracted the heat of hydration predictions from the machine learning. I plugged them in the finite element software that we've been using, and the prediction for the internal temperature is in orange, which matches very good with the sensor data. The final task that we wanted to work on is provide GDOT with easy to use and implement tools for initial decision making. And we have resorted to nomograms because, as I said, they are easy to implement, anyone can use them, and they are more flexible than other models. We have provided them with nomograms to find the maximum theoretical concrete temperature, and this would be a conservative case scenario. We have provided them with cost nomograms for pre-cooling using liquid nitrogen, and also 2 detailed nomograms to find internal temperatures in a no cooling case and a post-cooling case. And here I will only quickly just show what these nomograms look like. This one shows the worst case scenario for any concrete, and it depends on the temperatures of the different constituents of the mixed design, as you see here, and also the initial placement temperature of the concrete. And this was created for a baseline concrete using a type 1-2 cement only, and we would need to further modify this in order to include different options for different cementitious pastes. Some of them would be higher heat, like this one, medium heat, or lower heat, to give them more options. And this second nomogram that I'm showing shows the internal temperature for a specific mass concrete structure. And I'm saying specific because this nomogram takes into account the dimensions of the structure. So here we have the heat transfer area, here we have the volume of the structure, and then we have the initial placement temperature, and we would get the maximum temperature expected inside the structure. This is an improvement from existing nomograms in the literature or in the specifications because it takes into account the dimensions of the actual element, thus making it more specific rather than just giving a general prediction. And Yeah. One more thing I would like to add about these nomograms is that they could be used either forward or backward. So we could start with the temperatures of the different constituents and find the maximum expected temperature, or we could start with the goal temperature that we are looking for, and then find what temperatures of the other constituents we should have to meet this goal. So to conclude, I have shown how decision-making for mass concrete projects relies on first proper modeling when selecting a proper model for the temperatures and heat of hydration prediction, and also on optimizing the material selection for a certain project. I've also shown how machine learning can be used to enable high fidelity modeling of heat of hydration of different cementitious spaces and at different temperatures, and how it applies well when upscaled for mass concrete application. And I've also shown that how we have created some nomograms for GDOT and how they can be used as a fast and reliable method for initial decision making. And thank you very much.